Bismillahirrahmanirrahim. Dear students, grade 12, lecture number 41 and chapter number 16, the aesthetic behavior of acetylene. In the last lecture I gave you introduction about this one. Now these are the examples that how terminal of the acetylene give the aesthetic behavior and what are the uses in the chemistry, the analysis. So we can differentiate between the acetylene, ethene and ethane by using this test, by using the terminal of the acetylene group. Again I am going to revise this terminal because of in the alkynes there is the sp hybridization, especially terminal hydrogen means the carbon attack with this hydrogen in the last carbon. So this is the terminal. 50% S character and 50% P character, and it can be renders the carbon and pulls electron more strongly, making the attached hydrogen. Carbon pulls electron more strongly, making the attached hydrogen. So the hydrogen becomes slightly acidic. Partial negative charge creates and partial positive charge creates. Last time I told you this one. So this can be substituted by the metal. So now here the example is when the acetylene reacts with, this is the acetylene, terminal hydrogen, propyne also propyne, one carbon atom. This is the partial negative charge and this is the partial positive charge. You can use propyne with the terminal hydrogen here. So it can react with ammonium solution of silver nitrate. Ammonium solution of silver nitrate. Silver nitrate is added with ammonium hydroxide. We call ammonium solution of silver nitrate. And I told you that there is a substitution of terminal hydrogen. There is a substitution of terminal hydrogen. So you are seeing here is a carbon with the hydrogen triple covalent bond, and same case on this side also this carbon with a triple covalent bond, there is a hydrogen. This is also called terminal. So the product you will get, hydrogen is substituted by the metal silver. Like this one. This is called a disilver acetylide. You will get acetylide, propyl acetylide. So this is the acetylide, disilver acetylide, and this is the white precipitate. Disilver acetylide form a white precipitate, unstable. This one compound is going to be formed here, and also you will get 2 moles of ammonium nitrate. Ammonium hydroxide changes into ammonium nitrate and plus water. So this is the disilver acetylide. Alkenes will not give a test. If you have a ethene, propene, butene, so if you put the ammonium solution of silver nitrate, there will be no white precipitate. Even if you have a 2-butene, if there are 2 alkyl groups in between, there is a double covalent bond. In the last time I told you like this one. There is no terminal hydrogen. No terminal hydrogen is there. So this will not happen here. The test will be negative in this case. So must be the terminal of the alkyne. So this will be happening if this happens. If there is a hydrogen, this chemical reaction is going to be happening, and you will get the white precipitate of disilver acetylide. So another one. There is also another test. If you have this chemical in the laboratory, this is the terminal alkyne, both sides. You can use propyne also. So instead of ammonium solution of silver nitrate, you have to use also here the ammonium solution of cuprous chloride. Ammonium solution of cuprous chloride. So when you use ammonium solution of cuprous chloride in the acetylene or propine, then you will get a copper dicopper acetylide. Copper acetylide. So this will give a reddish brown precipitate. Reddish brown precipitate. So this reddish brown precipitate indicates that there is a terminal hydrogen with the alkyne or propine, and also ammonium chloride, because there is a cuprous chloride. So ammonium chloride is going to be formed, and also water is going to be formed here. Like this one. So dear students, these are the two tests to differentiate between the alkenes and alkynes and also alkanes. Alkenes do not give the test, and if there is a low terminal hydrogen with the alkyne, also the test will be negative. So this alkylides or acetylides used for the preparation, purification, separation and identification of the alkynes which contain terminal hydrogen. So these are unstable. These alkylides are unstable. So they are going to be changed into respective alkynes by using a dilute acid. By using dilute acid, suppose you have the silver, disilver acetylide, white precipitate. This is a white precipitate disilver acetylide, and you are going to put the sulfuric acid dilute. So you will get again acetylene and silver sulfate. So this is the separation, preparation, identification, purification. Suppose, dear students, if you have some impurities, in the acetylene, suppose ethane gas is added or ethene gas is added. If there are some impurities and we want to purify it, we want to separate it, we want to identify it, just add a silver nitrate ammonium solution. So only the ammonium solution of silver nitrate reacts with the alkyne which contains terminal of the hydrogen, which is act as an acid. So this will give a disilver acetylide white precipitate which is unstable, and you have to add the dilute acid to give again acetylene, and this will be a pure form because of the reaction which does not take place with the other impurities of the ammonium solution of silver nitrate as well as ammonium solution of cuprous chloride. So this test is used for the preparation, purification, separation, identification of the alkynes. Very important test, you have to remember very well. So dear students, this was the substitution reactions where the terminal hydrogen acts as an acid. Now because of the alkynes are highly unsaturated, carbon-carbon contain triple covalent bond, 1 sigma bond and 2 pi bonds, so addition reaction taking place. Alkynes undergo addition reactions in the analogous of the fashion of those of alkenes. The high electron density of pi electrons around the carbon atoms make them nucleophilic. I told you nucleophiles, rich electron, more electrons, nucleus slurring. So they can give the electron towards the electron deficient, which is called electrophile. So this acts as a nucleophile. Second number, two factors influence on the reactivity of the alkynes compared to alkenes. If you have alkene and alkynes, so there are two factors which influence for their reactivity. Number one, increase the nucleophility of the starting pi system and stability of an intermediate. For example, there is a carbocation or also carbocations. Carbocation or carbocations. So dear students, you done the addition of hydrogen when you done for the alkanes. Alkanes, for the preparation of alkanes, there was the addition of hydrogen we call hydrogenation because it is highly unsaturated. Addition reactions. This is the alkene and alkyne. Alkene contain double covalent bond, alkyne contain triple covalent bond, and you are going to put hydrogen. And the catalyst is first. If you use the nickel catalyst, 250 to 300 degrees centigrade, 100 atmosphere pressure, the chemical reaction is exothermic. About 195 or like this 219 kilojoules per mole amount of energy is going to be involved in this process if you bag for the hydrogenation of the alkenes or alkynes for the preparation of alkanes. Now, so in this case, you will get alkene. This is the ethine, acetylene, and you will get ethene. The chemical reaction is continuous. You can't prepare the alkene in this method separately. The chemical reaction doesn't stop. So eventually you will get the alkane. Same conditions. So you will get ethane. And the chemical reaction will stop because of no more addition of hydrogen is required and valency of the carbon both sides is going to be satisfied. So this is the hydrogenation, addition of hydrogen in the presence of nickel as a catalyst, and we call it Raney nickel. You done in the previous section. Raney nickel we call it, or you can use platinum or palladium. Dissolving metal reduction. Dissolving metal reduction. We are talking about the addition reactions. So dear students, if you have alkynes, so alkynes can be reduced in its addition of hydrogen to give a trans alkenes by using sodium ammonia solution. By using sodium ammonia solution, there is a reduction. Like this one. These reactions conditions do not reduce alkenes, hence the product is alkene. So the reaction proceeds via single electron transfer from sodium coming from the hydrogen from the ammonia. These reaction conditions do not reduce alkene. Means if you are using alkene because still there the pi bond, double bond, and you can say that it can reduce to make alkane. This chemical reaction doesn't happen. Alkene cannot be reduced by using this reason. Only the alkynes can be and reduce, and you can prepare the alkenes by using this method. Then you done in the previous section reaction of alkynes with hydrogen halide, hydrohalic acid, hydrobromic acid, hydroiodic acid, hydrochloric acid. So dear students, this is symmetrical, both sides contain one hydrogen, this is unsymmetrical. So it's you have a choice to add. So in this case, one hydrogen is added here, and this is called a vinyl bromide. I told you earlier. Vinyl bromide. Now you have a vinyl bromide, this is unstable. Vinyl bromide. If you now add the unsymmetrical reagent, again hydrobromic acid, so now the situation has changed. Now you have seen that this alkene containing the functional group bromine and double bond here, so there is an unsymmetrical one. This carbon has one hydrogen and this carbon has two hydrogens. Different hydrogen atoms are attached. So when the different hydrogen atoms are attached with the two carbon double bonded, when you add unsymmetrical, then I told you in the previous lecture, the rule we called Markovnikov's rule. So according to Markovnikov's rule, this bromine must be attached to the carbon which has a less number of hydrogen atoms. So you will get this rule is called Markovnikov's rule. So according to Markovnikov's rule, if you have unsymmetrical alkene and unsymmetrical reagent, the negative part of the unsymmetrical reagent attached to that carbon atom which has a less number of hydrogen atoms or low number of hydrogen atoms. Okay. So this carbon, I told you there are two types of carbon done before. One is called vicinal dihalide. Vicinal means two carbon atoms which are neighboring with each other and they contain the halogens. Vicinal dihalides we done before. And here the two halogen attached with the same which we call geminal. So this is a geminal. 1,2-dibromoethane. So 1,2-dibromoethane is going to be formed here, which is called geminal. Same case you done the before for the alkenes. Here is also addition of the water we called hydration. Hydration. Addition of water. This is the alkynes. I already discussed in the previous lecture that water is a polar and alkyne are non-polar. It is insoluble, does not dissolve. We have to use conditions. The conditions are mercuric sulfate and sulfuric acid, 75 degrees Celsius. Mercuric sulfate as a catalyst. This is a mercuric sulfate, dilute sulfuric acid, and 75 degrees Celsius. So mercuric sulfate as a catalyst, you have to acidify sulfuric acid, then there will be a hydration. So hydrogen will be added here terminal because both hydrogens are same. So you will get a CH2 double bond CHOH. Same nature of this one and this one, only functional group is different. This was a vinyl bromide and this is called vinyl alcohol. Dear students, vinyl alcohol is unstable. Vinyl alcohol is unstable. So there a rearrangement of this one. There will be a rearrangement. Now how the rearrangement taking place? So one of the hydrogen, this hydrogen is going to be attached with this carbon. So double bond is removed to make a alkyl group, methyl group. So double bond is removed and this hydrogen is gone and this double bond is shifted between carbon and oxygen. Between carbon and carbon, double bond shifted between carbon and oxygen and you will get a functional group, which is an aldehyde. So this is aldehyde functional group and you will get acetaldehyde. So from the alkynes through vinyl alcohol, we have the acetaldehyde. So acetaldehyde is going to be reformed here. This process is called hydration. In your book also written, vinyl alcohol is, I told you, unstable. It has a hydroxyl group attached with a carbon-carbon double bond. So it's going to be isomerized, rearrangement, isomerized. So except acetylene, all other alkynes give ketones. So this is aldehyde, and he say other alkynes are going to write also. Suppose you have propane, he said other than ethine, other than acetylene. Only acetylene will give aldehyde. This is from acetaldehyde. All other, he say all other alkynes give ketone. This is a propane. So if we use propane here, and same conditions, same reaction. This is the hydration, water. The conditions mercury sulfate as a catalyst, dilute sulfuric acid 75 degrees centigrade heating. So this is now unsymmetrical. You have to use Markovnikov rule there. This carbon has a low hydrogen and this carbon has hydrogen. They are very satisfied. We are not more between carbon triple covalent bond. So Markovnikov rules, this hydroxyl group will be here and hydrogen will be here. So dear students, you will get CH3 and this carbon and this is the OH and the carbon triple bond is into carbon double bond and there will be a CH like this one. 2-hydroxypropene and these vinyl groups, they are unstable, so there will be rearrangement. So what rearrangement is? This hydrogen shifted towards the here carbon and this double bond pi bond is shifted between the carbon and oxygen. This hydrogen attached to the OH group, just like before I told you for the rearrangement of this one, that this hydrogen is going to be attached there. Same is for this one. This hydrogen was attached to this carbon and you will get the aldehyde. The same case, this hydrogen containing OH, so this hydrogen will attach CH2 to make a CH3. This double bond is vanished and this pi bond shifted between carbon and oxygen. I am writing here. So there is isomerization or rearrangement. We call isomerization or rearrangement. So this is a CH3 already here. There is a carbon. So this carbon containing oxygen, I am writing here up. So this is a ketone functional group and there is a now CH3. This is acetone. So only the acetylene, ethylene give the aldehyde, rest of the all alkynes give ketone. So there is given here. Addition of the halogen in presence of carbon tetrachloride and the temperature is minus 34 degrees Celsius. All the chemical reactions are addition reactions. Addition of bromine water, reddish brown color liquid, in presence of carbon tetrachloride as solvent, minus 34 degrees Celsius. There is no doubt they are symmetrical alkynes, and bromine is also symmetrical. So you will get 1,2-diabromoethene. So this 1,2-diabromoethene is again brominate, same conditions. So you will get tetra. 1,1,2,2 tetra bromoethane, and this is also test for the unsaturation, because the color of bromine water is going to be discharged. Chlorine and bromine at acetylene triple covalent presence of reverse acid catalyst. The halogenation may be stopped at the dialkenes here. He said the chemical reaction may be stopped here, may be stopped. At this stage, double bond of dihaloalkene, which dibromoethene, is less nucleophilic than even triple covalent bond. According to research, maybe the chemical reaction is stopped and you will not get this product, but there are double bond addition possible, so there is a chances for this one. Students, the last reaction for the alkyne addition reaction is ozonolysis. When ozone reacts with alkyne followed by the aqueous work, get carboxylic acid. So there is a last reaction, ozonolysis. So there is alkyne. This is the alkyne. So when you are going to put the last ozone gas, the condition is hydrolysis is taking place. So during the hydrolysis, there is a cleavage. This bond is going to be broken down, and you will get a carboxylic acid. Two same molecule of carboxylic acid are going to be formed here. So this is about the unsaturated compounds, alkenes and alkynes. Dear students, now we start another very important section of this chapter. This is a long very chapter, and this is now we are going to start the aromatic hydrocarbons. Aromatic hydrocarbons. Aromatic hydrocarbons. So, in aromatic hydrocarbons, we discuss benzene. Benzene and its substituted benzene, when other groups are going to be added with the benzene by the substitution of the hydrogen atom. The benzene was first discovered by Michael Faraday, and it was isolated by the Hofmann, and the molecular formula of the benzene is C6H6 highly unsaturated compound. The molecular mass is 78. A special feature of the aromatic benzene is a resonance, we will discuss. And mostly the chemical reactions are substitution reactions. I am going to tell you that if you are, we are going to write the structure of benzene. So this is the structure: alternate, delocalized, 3 pi bonds, highly unsaturated, symmetrical, high unsaturated planar structure of the benzene. So this is the highly delocalized. So we think that being a highly unsaturated, 3 double bonds are there, so many addition reaction taking place. But according to the evidence, experimental evidence, that addition reaction with benzene are reluctantly. The benzene feels reluctant towards addition reaction. But benzene feels frequently substitution reactions, and substitutions, electrophilic substitution reactions. One electrophile substitutes another electrophile. These reactions are called electrophilic substitution reactions. Electrophiles are electron-loving positive charge. Okay. So benzene feels reluctant for addition reactions, and benzene feels frequent substitution reactions. So these are the electrophilic substitution reactions. Michael Faraday discovered benzene in 1825. Michael Faraday discovered benzene in 1825 during the destructive distillation of the vegetable oils. In absence of air and high pressure and very high temperature, if the organic compound, coal tar and other like other compounds, they are going to be heated at very high temperature and absence of air and pressure, we call destructive distillation. So the Hofmann used in 1825 to prepare the benzene from vegetable oils. Hofmann isolated it from the coal tar. So one thing I'm going to explain, then I will stop lecture here. Dear students, 1, 2, 3, 4, 5, 6. All the carbon have equal. All carbon has equal nature. That's why benzene gives a mono substitution reactions. Just I'll give you example. If you put here chlorine, this is also called chlorobenzene. And if you are going to put chlorine here, this is also called chlorobenzene, no difference. If you put chlorine here, this is also called chlorobenzene, no difference. This is called mono substitution reactions. But dear students, if you have an alkane, if like this one, if chlorine is here, this is called 1-chloropropane. 1-chloropropane. But if you are going to put the chlorine here, this is called 2-chloropropane. You will get isomer, 2-chloropropane. There are two substitutions here. Two have different names. But in the benzene, you put chlorine here. There are mono substitution. This is the property of the benzene. All carbon atoms behave alike, same, no difference. That's why called mono substitution. This is called chlorobenzene. Chlorobenzene. If you put the alkyl group here, this is called methyl benzene, or we call toluene. We call it toluene. This is toluene, CH3 add toluene. If you add nitro, this is called nitrobenzene. If you add hydroxyl group, this is not alcohol. Arene, benzene is arene, aromatic. This is a phenol. Phenol, carbonic acid. Which is used as disinfectant in the medicated soaps and also Dettol. This is a phenol carbonic acid. And if you are going to change the functional group, you have NH2 aniline. This is the aniline. And if you are using aldehyde, benzaldehyde, benzaldehyde. If you are going to put COOH, this is called benzoic acid. So in your book, all these are mentioned here. So in the next lecture, if there are some remain, so I will explain nitrobenzene and also toluene, also styrene, benzoic acid, cumene. There are many. So in the next lecture, I will explain. Then we have to discuss dye substitution. When the two groups are attached, then what happens? Thank you very much. We stop.